So the daily problem is daily temperatures. It says, given an array of integers temperatures, return an array answer of the same length. That is the number of days you have to wait for there to be a warmer temperature than the current one. So if we look at the input-output in the examples, the first day we're given 73, the second day we're given 74. So we know that and's at 0. The first element is going to be 1 because it takes 1 day to find a warmer temperature. Same with and's at 1, but then 75 was a local maximum, and then it looks like the temperature goes down, and we have to wait till 4 days later to find a 76. So this problem, I think, is really good at dipping your toes in the water for monotonic stacks, because it's a monotonic stack. It's a stack that doesn't really require the full magnitude and confusingness of monotonic stacks, which are notoriously complicated and weird. But it's basically the same concept. And I think that makes this a really good problem to follow along with, and a really good daily problem in general. So let's reset the code definition here. So the first thing that's always good to do is say n is the length of temperatures. It's good to do that for, among other reasons, to kind of keep track intuitively of your time complexity, because then you kind of have this convenient n for O of n notation. And then we know we're going to have answer is going to be an array of zeros times n, and generally it's going to be an array of zeros or an array of none if we know that we're going to assign every element. But actually here, this is kind of convenient right off the bat, because it says if there's no future day where this is possible, so if it's the hottest day, like the 76, until the end of time given to us, then return 0. So we can also see that the last element's always going to be 0. But it's nice because this means that we don't really have to, we can just set the default to 0 and then set it to not be 0 when the time comes. So I've spoiled it a little bit. This is something that requires a stack. Maybe it doesn't require, but it's good to use a stack. So I like to use DQs. And this is where the sort of monotonic stack aspect comes into it. If, for example, we looked at the solutions section and saw a bunch of things that said stack, so we know, okay, we're probably going to want to use a stack. How do we use it? It's a really good exercise, and you might even want to just pause and think about, like, how could you use it? Do you iterate through forwards or backwards, or do you put everything into a heap and use a stack somehow that way to get a local maximum or minimum? Do you want to translate this data somehow? That's what a lot of monotonic stacks do. They would count forward and say, change this element to be the previous element under some condition. It turns out it's actually very straightforward here once it's all explained. So all we really need to do is say for I in range n. And then let's start out with just like stack.append I. So we're gonna, right now all this does, if nothing else happens, is the stack is gonna be filled with everything. And then what happens when we reach a certain element? Let's say we count through, we say, okay, the stack has 73, 74, 75 is on top. I is now 3. Temperatures at I is 71. 71's the 3th element. Before we append it to the stack, is there any way we can figure out ands at 3? Can we figure anything out with the 71? No, because we haven't gone past it, but we can look at the previous elements and say, hey, you know what? If element 2, let's say it was 70, 71 suddenly just immediately gives this answer. It's 1. And similarly, like let's say we reached 75 here, let's go back in time and say, okay, the stack has 73, 74. Now there's 75. We know that the 74 is going to be 1. So we can just pop that from the stack. We're never going to need that ever again. And then past that, we can say, hey, 73 would be 2 if 75 was the first thing that's greater than it. And then if we go back to 74, maybe it's a little bit of a confusing chronology here, but the moment we reach 74, we know that 73 is going to be 1. Nothing past that will ever matter, so we can pop it. Because yes, we reach 75, which is also greater than 73, but 74 is the earliest one, which is all we care about. So all we really need to do here is just reach an element. Bad example because it's the lowest. Reach an element and then just look at everything past it in the stack and pop that and say 76. Hey, 72 is 1 backwards and it's lower. So set ands at this index to be 1. And then 69 wouldn't actually show up anymore under these rules because we would have encountered and popped it at 72 and we would have set 69 to be 1. And we can see that that holds true here. And then 71 would have been popped at 72. It would have said, okay, pop 69, great. Now pop 71. And then, oh, you reached 75. Well, I guess just stop because there's nothing we can do. But then when we hit the 76 and we're looking backwards, we're going to hit the 72. These will have been popped when we reached 72. And then we'll see this. So then we can say, okay, great, we found the first element that's greater than 72, which is 1 later, and the first element which is greater than 75, which is 4 later. And this is actually why we're appending I instead of, you might think to append temperatures at I, but we don't really need to do that. We can just always say temperature at I or temperature at J or whatever to access that. But it's this way we also are keeping track of where it is. And we do that because, for example, when we pop 72, we're saying, okay, I is 0, 1, 2, 3, 4, 5, 6. 72 will be stored in the stack as 5. So then we just say, oh, well, ands at 5 is 6 minus 5. Or ands at 3 is, or 2 is 6 minus 2. So all we say is while stack at -1. So while the last thing in the stack is we actually want to say while temperatures at stack at -1 is less than temperatures at I. Among other things, stack.pop, because we never need to think about that again. But also ands at stack at -1 equals stack at -1, which is the index I minus stack at -1. So for example, at 76, we would say, hey, I is 6. When we reach this, we say, well, stack at -1 is 5, and the fifth element in temperatures is 72, which is lower than 76. That's what this is saying. Then we say, all right, well, then we immediately know what answer at 5 is going to be. It's going to be 6 minus 5 is 1, because 6 is 1 element past 5. And similarly, 6 minus 2 is going to be 4. And that's how we'll arrive at this. But we also have to say, because we could reach, for example, 76, the highest point in the stack, that'll just count backwards until the stack is empty, and then this will throw an error. So we need to say stack and, well, the stack has anything, and the thing in the stack is less than. And then all we need to do is just say return ands. Not the fastest, but it's a good proof of concept.